Now, what if we don't have the actual function to work with, but they give us some information? So what we're going to do here is try to make a good sketch of the graph just based on what they're telling us here. So for this first one, we have f prime of x is more than 0. So we have a positive first derivative on these two intervals here. So negative infinity to negative 4 and 2 to positive infinity. So what this tells me is if I'm graphing f of x right here, what this tells me about f of x is that we are increasing on these two intervals. So what I'm going to do is just kind of draw these changing points. So negative infinity to negative 4, and then 2 to positive infinity. And what they're telling us is over those intervals, we are increasing and increasing over here. We don't know what's happening between negative 4 and positive 2 yet. And that's the next statement. F prime of x is less than 0 on the interval negative 4 to 2. So what that tells me is that we are decreasing on that interval. And then they don't tell us anything else. So what I'm going to do is, if we're doing, or as we go across, so we're going increasing, then decreasing, and then increasing, what I'm going to think is we'll have a local maximum right here at that changing point, and then a local minimum right here at that next changing point, with how we're changing between increasing, decreasing. But without any other values, there's no points to plot. Instead, I'm just going to kind of make up where these happen. So make a local maximum there, and then go to decreasing. Make a local minimum here, then switch to increasing, and then continue on forever with those. So with just information on increasing, decreasing, and without any other points, that's a good sketch right there. It matches what they told us. And with that, we made some relative extrema just based on how increasing and decreasing change between each other. Okay, this next one, f of x is increasing and concave up on negative infinity to 0. So negative infinity to 0 is to the left here. We have increasing and concave up. And something to think about is when we have concavity, so concave up is this shape, and here's our local minimum. We have two trends here. The right-hand side of this, that shape is with decreasing, whereas the right-hand side is the increasing. So what I'm seeing on the left-hand side of this graph is more of this shape, the right half of this parabola. So I'm seeing is something that looks like this on the left-hand side of the graph. Then what we're told is f of x is increasing and concave down on 0 to infinity. So similar idea with this has two trends. We have increasing side of it and a decreasing side of it. And what we're looking for is that decreasing side. So it said increasing. We're looking for this increasing side. So what I'm seeing is over here, something increasing and concave down. So with that, I just have this general idea of, okay, concave up and increasing, and then concave down and increasing, and then they're going to switch over. So at this changing point at x equals 0, we're going to have an inflection point. But it's not a local minimum or maximum because we're going from increasing and then still increasing. So I'm going to do is get that concave up shape and increasing, and then we'll switch to kind of curving downward but still increasing. And that would be our shape. Okay, one more here. So use information about the first and second derivative to help you graph. So this case is giving us the function, so we're going to kind of go through what we did in the last video to get an idea of what is happening with our function. And what we could go ahead and do is start by finding horizontal and vertical intercepts for our function, because plugging in zeros is pretty nice. So if I plug in 0, we're going to have 0, 0 as a coordinate. So just to get a point to plot without plugging in other values, we have that going for us. Okay, our first derivative would be 2/3 x to the negative 1/3. So we're dealing with the 2 over 3x to the positive 1/3. And what I want to make note of here is that we're undefined at x equals 0. We cannot plug in x equals 0 there. And with that, we're not going to have any other critical points, because if I try to solve for where this equals 0, I'm going to start by multiplying both sides by that 3x to the 1/3, and we're just going to end up with 0 equals 2, which is a false statement. So what that tells me is that there's no critical points. But what we do have is a point where we're undefined. So what we're going to do is, for our increasing decreasing table, is we're going to use this as a changing point. That will also be included with our tables where we have our critical points, but we also include any spots where our first derivative is undefined. So I'm going to go negative infinity to 0, and then 0 to infinity. I'm going to evaluate the first derivative at a negative 1 and have a first derivative at a positive 1. If I plug in negative 1, that should be a negative 2/3. So it's negative, so we are decreasing. If I plug in a positive 1, that'll be a positive 2/3, so we are increasing. So we have the point at 0, 0. We also know that's going to be where we change trend. And what we just found is that we're decreasing on the left-hand side, increasing on the right-hand side. Let's take a look at our second derivative. So let's use that 2/3 x to the negative 1/3. So that's going to be a negative 2/9 x to the negative 4/3. So our second derivative is going to be a negative 2 over 9x to the 4/3. And we're going to run into the same scenario. If I plug in 0 and try to find any inflection points, it's going to come up with a false statement. So no inflection points. But we run into the same scenario where we are undefined at x equals 0. So making our concavity table, that's going to be the only changing point that we have. Negative infinity to 0, 0 to infinity. Let's take a look at that second derivative at negative 1 and second derivative at positive 1. And this one's going to be a little interesting because, as a refresher, we can write this in two ways. I'm going to change this to our radical form. So this is taking the third root of our value x raised to a fourth power. And that fourth power can either be inside or outside. It should be treated the same. So when I plug in a negative 1, I'm raising it to the fourth power. So that's going to make it positive, 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 and then we have that negative out front. So when we simplify, we're going to get a negative value out. So this is concave down. And when I plug in positive 1, the same thing is going to happen, because 1 to the fourth will also be a positive 1. So we're going to see the same trend. So we're seeing concave down on both sides, but we're seeing different parts of this concave down parabola. Over here, it's concave down and decreasing. So we're seeing this kind of part of the parabola where we're going downward. And then over here, we're increasing and concave down. So we're seeing this part of the parabola, this left-hand side. So what I'm seeing is, I'm thinking our function will have concave down, and then we're going to get to that point 0, 0, and then we'll have concave down, but increasing. So concave down and decreasing. concave down, and increasing. And it should be a little more symmetric than that, but hey, it's a sketch. And there we go. And then that's just showing that we don't have an inflection point because we're not changing concavity. We also don't have a derivative there because it's a sharp corner. We can't evaluate the tangent line just at that spot because it's such different trends on either side. So there we go. That one was given a function, but then the others we can get a decent sketch going just with some information about our derivatives.